Hello everyone, very good evening. So once again, welcome. So let's begin for the day. We'll take some basic questions. Okay. Yeah. What are the okay, yeah. What are the techniques? What are the techniques used for sampling? What are the techniques used for sampling? And what is the advantage of sampling techniques? What are the advantages of sampling techniques? What are the techniques used for sampling? So we all know that, data science, data analytics, it involves the task of transforming the data, right? So when we transform data, we do a lot of changes, and those changes have to be accepted here. And these changes, we are working on sample. And why is the sample important, and what are the techniques we can use for sampling? So data science involves various technical analysis methods to extract some meaningful insights, right? Using which a data analyst can apply to their business scenarios. So it deals with checking your existing hypothesis and information, and also it will answer questions for a better understanding, better business related decision making process. So data analyst mode maximum, it focuses on getting present meaning from the existing historic context, whereas data science focuses on predictive modeling. So when this process starts, a data analysis cannot be done on whole volume of data at a time, especially when it involves very large data sets. Very few organizations, they get involved with population, but whenever we talk about population data or sample data, right, we need resources to perform some analysis on it. So while doing that, it's very much necessary to carefully take sample data out of huge data, and that should represent your actual entire data set. So basically, to put it in a small phase, we have techniques, which is a probability sampling technique. The first one, we have probability sampling technique and non-probability sampling technique. So why are you using sampling? Because we don't have enough resources to work with population data. When we want to work with population data, this is not a right procedure here, because a lot of time is taken, and for data pre-processing, analyzing the data, it takes a lot of time. So definitely the choice is picking the sample, work on it, generalize your results on population. Generalize your results on population. So what are the different techniques you can follow? Whatever we are talking as a probability sampling technique, the default technique what we use here for this, the default technique what we use here for picking up a sample, we have the blindfolded technique. So what you call it as blindfolded, it's a default technique, right? So it is nothing but your simple random sampling. Always this is our choice of picking the sample. You always go for simple random sampling only. Okay, when we are talking about simple random sampling, this comes under, you are giving equal chance to each and every data set, data point, not data set. Every observation is very, very important for you, and you give equal choice, equal chance to each and every observation here. So when we are taking every observation here, we are saying that this falls under probability comes into picture, and the name you give is probability sampling. It is also called as unbiased sampling, right? And you're also calling it as SRS technique. These are the broader classifications. Actually, non-probability and probability sampling are the broader classifications. The difference just lies in between above these two, non-probability and probability, is that the sample selection process. If at all it is randomized, and if it is not randomized. With randomization, when you go for random word, there is a chance given to everyone. Every element, every particular observation is getting equal chance to be picked up, and there is a chance that these are a part of our sample. When we talk about non-probability sampling, the other way around, it is not giving chance to each and every observation. Okay, then this is an advantage because you're generalizing your results onto the population. We are having the concept of sampling funnel, and it is nothing but inferential statistics. So the sampling technique uses randomization to make sure that every element of population get an equal chance to participate as to be a part of selected sample. So it's alternatively called as random sampling, right? In this, if at all I divide them in probability sampling, you have simple random sampling, you have stratified sampling. And also you have cluster sampling, right? In non-probability, it does not rely on randomization. So it is convenience sampling, it is purposive sampling, and it is quota sampling. Or you can put under snowball sampling, right? So there are many techniques are there. Depending upon the data we have with us, we will go and use them. Okay, the next question here is, okay, list out the conditions for overfitting and underfitting. Right? So if we will know the first one, overfitting. So the model performs well only for your sample training data, right? How would you answer this question? Overfitting and underfitting is a concept which we have every time, and the concept is very, very important, and you should be having a clear cut explanation on this, why it is, how it is, what are the techniques involved in it to solve this problem, because this is our friend. It is carried away every time, and we always have the problem of overfitting, but we should know that what is the solution for this, right? Underfitting is a problem which we can fix that problem very easily, but overfitting is something which we can't do. It takes time for solving the problem of overfitting. So what is this overfitting? When the model performs very, very well, okay, the model performs well only on sample training data. When you have your split happening and you have your sampling training data, it performs exceptionally well on this. If the problem starts when a new data is given as input to the model, it fails to provide any results. Okay, it will provide wrong results or worst results. The accuracy on this is very, very worst. This condition occurs due to a consequence which is called as low bias and high variance. Right? So overfitting is, it tries to learn everything. However, you have the pattern, it tries to do a classification like this, right? It tries to fit in very, very properly, and it learns the pattern. Overlearning is happening in overfitting. But when it comes to the another, that is underfitting, the model is so simple that it is not able to find out the pattern. It does not perform well, not even on this training, but also on the testing also it becomes worse. This is due to, underfitting is due to high bias and low variance. So linear regression is a model, machine learning model, which is more prone to underfitting. Which is more prone to underfitting. Right? So how do you fix this? There are many regularization techniques involved here for solving this particular problem. How do you solve this bias and variance problem? Bias and variance, high bias, low variance, or low bias, high variance problem here. There's a trade-off, right? Every time you do some changes here, the changes will impact your accuracy of your model. But when this is going to happen, you should not make your model learn the patterns very, very dominating way, and you can't make them worst also. Okay, so how is it is going to happen here? Whenever you have the difference between your, what is a bias? If you answer that bias and variance, they'll ask you what is bias. Bias in simplest term is that predicted value and actual value, expected value, otherwise you can call it as an expected value. Right? The model makes certain assumptions when it trains on the data. The model makes certain assumptions when it trains on your data. When it is introduced, when the assumptions which you make on trained data, when you introduce assumptions, the assumptions what you introduce may not be always correct. The assumptions may not be correct. In our model, if we have large number of nearest neighbors, the model can totally decide that some patterns are not important at all. It can just consider that glucose level and the blood pressure will decide if the patient is having diabetes or not. This model would make very strong assumptions about any other pattern which is affecting your outcome. But you can also think a model where you are predicting, right? Some relationship is there. There might be some complex relationship between those two. You might have a very, very complex relationship here. So the input variables and the output variables, the relationship will go even more worse. So what is that now? That is bias problem. When we talk about variance now, right? There are a lot of fluctuations between your input and output. Right? The model will not learn much. It goes the worst on test data. When you're making it learn patterns, it works the best. Train. High variance. Too much. It learns too much on the training data. It works too much good on training data, but the worst on test data. Right? It works the worst on test data. So if we take the same glucose level, the number of people who are getting affected and they are diabetic patients based on the glucose levels. Right? So the glucose level is, if the glucose level is more than certain number, maybe certain number as 78, right? The blood pressure is less than 98. Right? You also take skin thickness. Skin thickness. You take one more input. Like that, you keep on adding the inputs. right? And decide based on his inputs the patient is diabetic or not. Decide the patient has diabetes or not. All other patients who don't meet this criteria also, they're not diabetic. This may be true for one patient, this may not be true for one other patient. There might be outliers in your data also. Maybe something got recorded incorrectly. This model would have very, very high variance error because the predictions of the patient being diabetic, right? And that is going to work very, very good on training. If to make it simpler and the relationship between all these inputs becoming very, very complex, right? And it makes your model overfit, right? Any model with high bias error underfits the data. It will underfits the data and make very, very simple assumptions on it. But when you have high variance error, right, it overfits the data. It learns too much. It learns too much. Here it learns less. A good model, which we want, where these two errors are balanced. Both errors should be balanced. Right? That's where you have the concept of bias and variance trade-off. Okay. So one more generic question now. Define confounding variables. Define confounding variables. So these confounding variables are also called as confounders. These are a type of variables where they influence both your independent and dependent variables. Both your independent and dependent variables, causing a very good association between them. And also mathematical relationship between those variables are associated. But casually they are related to each other or not, we don't know. And these are also called as confounders, as I told you. These are called as confounders, confounding variables. Right? We don't know, they are underlying data variables which impact this and this, but they are not openly seen for us. Right? We can't visualize them openly. It makes our data, we'll find the correlation and we'll not have good R-square value. Maybe we are entering into collinearity problem. Many other things come into picture because of this confounding variables. Okay, that is our confounding variable. Yeah. Next, our time series problems different from our time series problem different from other regression problems. We all know that time series is an extension of linear regression, right? Here also we have some terms, common terms, right? We have some common terms here, like extension to this, like autocorrelation, movement of averages, right? And having a y-axis variables for predicting a better future, right? There, anyway, you're calling it as a prediction. Here you're calling it as forecasting, right? Forecasting and prediction, it is the main goal of time series problems where accurate predictions can be made, but sometimes these underlying reasons might not be known. Having time in the problem does not necessarily mean that it becomes time series problem, but there should be relationship between target variable and time for a problem to become a time series problem. So the observations, what we take close to one another in time, they're expected to be similar, right? So today's weather would be similar for tomorrow, but not similar to the weather from 4 months. Sorry, from 4 months from today. So weather prediction based on past data becomes a time series problem for us, but it does not come under regression. And here for regression, we are using cross-sectional data. Here we are using time series data here. Okay, then one more important question. What is cross-validation? What is cross-validation? Sorry. How do you cross-validate and why it is very, very important? So definitely it is always a need for us to validate the stability of your machine learning model. You need some kind of what you call it as assurance, right? That your model has got most of the patterns from the data correct and it's not picking up too much on the noise, or it is on low bias and low variance side. So validation, the process of deciding whether the numerical results quantifying hypothesized relationship between a variables, they're acceptable as descriptions. So there's nothing but your validation. And error estimation for the model is made when you have already given training. Also, you call them as residuals, right? We have actual value, you will have predicted value, and you estimate whether it is the error is minimum or not. So this is what is required. Cross-checking again and again. Getting the idea about our model building is nothing but known as cross-validation. The remedy for all the problems, like whether it is performing well or not on the trained data and test data, right? And better pattern learning is happening or not, we go for cross-validation technique. First method you have here is hold-out method. It's a simple kind of cross-validation technique, which is hold-out method. It is nothing but your train and test split. Hold out. Certain percentage of data you hold out, like 80%, 20%. Which data points will end up in validation set, we don't know. Any 80% would come, 20% and 80% may come here and there. So this is because if it is not certain which data points will end up for validation data. It's a holdout, normal train and test split. What is k-fold cross-validation? By reducing the training data, we may risk losing important patterns and trends, which will in turn increases the error induced by the bias. In k-fold cross-validation, the data is divided into k subsets. If you divide your data as k equal to 5, part 1, part 2, part 3, part 4, part 5. Right? And other, first k equal to 5. So k minus 1 subsets will go for testing. Okay, means I can say that for every iteration, for k equal to 5 means you will have 5 iterations. Okay, the error estimation here is happening like this. So when you first k equal to 1, k, p1, p2, p3, p4, p5. This will go for test. All other will go for train. Then p1, P2, P3, P5. P4 will go for test. P1, P2, P3, P4, P5. P3 will go for test data. P1, P2, P5 will be your train. Like that, every iteration, the training is happening. Most preferable way here, why you will go for this k-fold cross-validation, the results are damn good when you have imbalanced data sets. When the concept is imbalanced data set. So imbalanced data sets are the data sets where one particular class is less than 30%. Now, if you have spam messages and ham messages, right? This ham and spam, 30% is here, 70% is here. You can call it as balanced. But sometimes if it is 29 and 71, you call it as imbalanced. That time, when you want to give training, more training would happen on spam emails. I think I wrote opposite. This is ham. This is spam. More training, less training is happening on spam. More training is happening on ham messages. Right? To contradict and give better training on both of them, whatever split you are doing, each and every iteration, one part is trained. So P5 is tested 5 times. It's trained 5 times, 1 time it is tested. P4 is also 4 times training, 1 time testing. P3 also, P2 also, P1 also. This significantly reduces bias as we are using most of the data for fitting, and also significantly it will reduce the variance as most of the data is also being used in validation data set. So interchanging of your training and test sets, it also adds an effective method of giving it training. Generally, most preferred is k is equal to 5 or k is equal to 10. But nothing is fixed here. Anything is your choice, what you can do. So in k-fold, the data is divided into k subsets. Hold out method only, it is repeated k times. Each time, k subsets. K means one part is used for, I think I told opposite way, right? K subsets is used for test. K minus 1 subsets are used for training. So the error estimation is averaged over all the k trials to get a better effectiveness of your model. Okay, this is your k-fold. And one more you have here, stratified. You have stratified k-fold. Right? This is also very, very large imbalanced data sets. And totally we'll go for stratified k-fold validation only. Right? Imbalanced data sets in response variables. For example, in data set concerning a price of the houses, there might be large number of houses having high price. Or in case of classification, same thing, cancer, no cancer. Less number of more number of no cancer, less number of cancer. A slight variation, same thing, but k-fold cross-validation technique is made such that each fold contains approximately same percentage of samples of this and this. So this much cancer means no cancer. It will divide it like that. Proportion is what it maintains. If k is equal to 5. Equal amount of no cancer, cancer, no cancer, cancer, no cancer, cancer. All the people, it selects like this. So this only it will make it. This part will go for training. This part will go for testing. Right? The mean response value is approximately equal in all the folds. This variation is also known as stratified k-fold cross-validation technique. Right? So validation techniques are also referred to as non-exhaustive cross-validation methods. These do not compute always the splitting the original sample. Right? This do not compute always splitting the original sample, but you have to decide how many subsets you want to make. So these are sometimes also called as exhaustive methods. The all other ways where you want for training data and testing data. There is one more which is called as leave P out. Right? Leave P out cross validation. Leave P out cross validation. This approach will leave P data points. P data points out of training data. N data points means N minus P. If you have N minus P would come for test, N would go for train. This is your validation data. Means P points. P points are used as dilation set. N minus, sorry, my bad. 1 minute. I get confused. N minus P are used for train. P is used for test. Right? This is repeated for all the combinations where original sample can be separated this way and then error is averaged for all the trials to get better overall effectiveness. If your P is equal to 1, it is called as leave 1 out cross validation. These are going to give very, very good results. Very, very useful technique for effective working of your algorithm, effective training of your algorithm, so that you can mitigate the problem of overfitting. It is also useful in determining the hyperparameter of your model. Which parameters will result in lowest test error? Right? So this is available in your scikit-learn package. Okay. Now, okay. What is the difference between covariance and correlation? What is the difference? What is the difference between correlation and covariance? How do you decide this? Covariance and covariance. These are the two terms which are used for establishing a relationship and dependency between any two random variables. Right? Correlation is something which is helping us to find out the relationship between y and x. But if at all you are taking a relationship between x and x, you call it as autocorrelation problem. Right? X and x, you are telling it is autocorrelation. Y and x, you are calling it as a correlation problem. So it's a technique which is used to estimate the quantitative relationship between two variables. It is measured. It is trying to find out how strong this is there and impacting your y. Right? How impactful is x variable in predicting your y? Right? And the correlation should be always greater than 0.85, which is nothing but your correlation coefficient, which is greater than 0.85 given with R, whose range is -1 to 1. Right? It is strong. If it is less than 0.4, it is weak. Anything between these two, you call it as moderate. Right? But when we talk about covariance, and one more thing is correlation, it does standardization and then gives a relationship. The good thing about correlation is, right, you are able to know whether the relationship is positive or negative or neutral. You are also able to know that magnitude wise, direction wise, linearity. Right? And also you are doing standardization to your data. But what happens with covariance now? This explains the systematic relationship between your variables, where the changes in one is affecting the other or not. Right? No standardization of your data is done. Right? So strength is what you can't find out. right? What we talk as linearity, direction, and strength, right? Here, there is no strength, means we can't find out the relationship, how strong the relationship is there, because there is no standardization done here. Okay, so correlation, if you know covariance, correlation can be calculated, right? Right? This is what you do. This is the difference between correlation and covariance. Okay, next, what are the available, okay, what are the available feature selection methods for selecting right variables for building efficient predictive models? So while using a data set in data science or machine learning algorithms, it happens that all the variables are necessary and they are useful to build a model. But something which is very important is that okay, not all the variables are necessary for us. We need to avoid few redundant models to increase the efficiency of our model. So there are three main methods in this. What is filter methods? First is filter methods. So what is that you do here in filter? Right? These methods pick up only the intrinsic properties of the features that are measured, or they're not cross-validated performances calculated. It's taken straightforward. They're generally very, very fast and require less computation resources when compared to any other wrapper method. That is the filter. Very, very easy, very quick. There are various filter methods such as chi-square method. Just now what we have discussed is a correlation coefficient method, right? You can go for mean absolute difference method, right? Dispersion ratios, right? So this is nothing but you do all the features, you apply some feature subset selection methods, and you pass it for learning the algorithm. Okay, then comes the wrapper methods. These methods need some sort of method such as to search greedily on all the possible feature subsets. You need to access their quality by learning and evaluating a classifier with the feature. So the selection selection technique is built upon machine learning algorithm on which given data set needs to fit. There are three types of wrapper methods here. One is a forward selection. Right? Forward selection. Here, one feature is tested at a time and new features are added until X1. You build a model like this. Right? Forward selection. So you build model, whichever is best fitted, you continue adding the features. Okay, best. Like this. You keep on adding the features until you fit your model in a proper way. Backward selection method, where you start eliminating. You eliminate one by one which are not good for estimation. There is one more, which is recursive. These features are recursively checked, evaluated recursively how well they are performing. So these require high-end resources for analysis. They usually lead to better predictive models. They're having high accuracy than any other filter method. Right? And then is embedded methods. Embedded methods. Embedded methods are nothing but they constitute the advantages of filter and wrapper interactions, both. But while maintaining some computational cost also. These are iterative. They take each model's iteration, carefully extract the features, right, which are contributing to the very good training. For example, you have your lasso. It comes under embedded method. Right? It is called as a feature selection method. You also call it as L1, shrinkage parameter, what it helps us here. And also random forest. These are the examples of embedded methods of feature selection. Okay, these are the wrapper methods, filter methods, and embedded methods. Okay, and then we have how will you treat categorical variables as continuous variables? Okay, we'll treating categorical variables continuous variables result in a predictive model. So categorical variable is a variable that can be assigned to 2 or more categories with no definite category ordering. Ordinal variables are similar to your categorical variables, but they have some order. So if the variable is ordinal, then treating the categorical variable as a continuous variable will result in a better prediction models. So categorical variables sometimes can be treated as continuous variables, right? You are converting them into ordinal data, and then you are making it continuous, which becomes numeric data, and then you just pass them as is to your model. Okay, then what is the difference between univariate and bivariate? Univariate and bivariate analysis. What is the difference between these two? What is that? So univariate is a data analysis where you are only doing one variable at a time. Here this analysis deals with statistical study of 2 variables at a time, right? And if the analysis deals with more than 2 variables, you call it as multivariate. So what is the example for one variable? Pie charts, scatter plot here, right? Studying the relationship between I can say humans, social media habits, right? Social media habits and their self related factors like age, number of hours spent, employment status, relationship status. You're trying to find out the relationship between these habits with the important factors: age, relationship status. That becomes your multivariate data, right? Multivariate data here. Okay, then finally, okay, let us understand few things with respect to this. Okay, feature selection. I missed one question. Let me write it here. Okay. How is feature selection performed? How is feature selection performed? Using the answer I already told you, but this is one more way they can ask you. Regularization method. Yeah, using the regularization method. Come on. So the method of regularization, it is nothing but we are trying to add different parameters as penalties for our machine learning model, for reducing the freedom of the model to make it overfit or to avoid the issue of overfitting, right? So feature selection is your lasso regression model. Lasso, the linear model, it will apply a penalty term for us. This penalty term is making your model solve the problem of overfitting, right? So when we are talking about lasso, it is nothing but feature selection method, right? So whatever we have talked, like low bias, high variance, high bias, low variance problem, we are choosing a right regularization parameter here, right, which will reduce your problem of overfitting, right? So both are powerful techniques, both are helping us here to solve some or the other problem, but lasso regression, you are adding a penalty equivalent to absolute value of your magnitude, right? Adds a penalty term which is an absolute value of your coefficients, which will make this. So why penalizing the magnitude of the coefficients here? It will directly take and it will penalize this coefficient. They make, beta 1, they make it to 0. Means it will automatically by default changes the coefficient values to 0. Okay, why? Because it's a feature selection method. The other way around is your ridge regression, which will make your beta naught values. It will make your beta naught values very, very minute, like negligible. Okay, they make it negligible. Okay, here but it makes automatically 0, right? So that is the thing what we are discussing here. So let me stop here. Thank you all for joining in, and let's connect next week same time. Thank you all.